Hello and welcome to Vodcast 15.2. In this Vodcast, I will overview the birth of modern astronomy. I ended Vodcast 15.1 by showing you this slide. And although I don't intend to spend much time in this Vodcast on this slide, I would just like to stress once more that Nicholas Copernicus was the first astronomer to propose a sun-centered universe, and he was the one responsible for ushering out old astronomy. At this point, I'd like to introduce Johannes Kepler. If it was Copernicus that ushered out old astronomy, it was Kepler who ushered in new astronomy. Johannes Kepler relied on the mounds of very precise data collected by Tycho Brahe. One of the key features to Brahe's data was that the orbit of Mars did not fit a circular path. Kepler trusted the accuracy of Brahe's data, and what he discovered was that planets' orbits are not circular, they're elliptical. And that includes our very own planet Earth's orbit. It's close to a circular orbit, but it's not a perfectly circular orbit. Another very important discovery of Kepler's that's related to the elliptical orbit of planets is that planets revolve around the Sun at varying speeds. When the planets get closer to the Sun, they'll move faster, and when the planets are further away from the Sun, they'll move slower. Planet Earth is actually closest to the Sun in January and furthest away from the Sun in July. So in our orbit, we're moving fastest as we approach the winter months in the Northern Hemisphere, and our planet is moving its slowest as we approach the summer months in the Northern Hemisphere. Kepler's third law is a quantitative proportionality, and it relates a planet's orbital period to its distance from the Sun. Now, the meter stick we typically use in astronomy is what's known as the astronomical unit, which can be symbolized AU. 1 AU is defined to be the average distance from Earth to the Sun, and that's a distance of about 93 million miles, or 150 million kilometers. So if a planet is closer to the Sun, it will have an AU measurement less than 1, and for planets that are further away from the Sun, their AU measurement will be greater than 1. Shown on the screen is some planetary data that includes both orbital periods and distances from the Sun. Kepler's third law states that the orbital period for a planet squared will be equal to the mean solar distance of the planet cubed. So I'd like to briefly verify Kepler's third law to you by referencing an example. Let's consider Mars, which has a solar distance of 1.52 astronomical units. Notice that the AU distance for Mars is greater than 1, and that's because it's further away from the Sun than Earth. Let's take that distance of 1.52 AUs and cube it. By utilizing a simple calculator, I see that 1.52 cubed gives us a value of 3.54. Now let's reference the orbital period for Mars. And the orbital period is essentially the time it takes Mars to go around the Sun one full revolution. You can kind of think of that as being a Martian year. Mars has a period of 1.88 years, and if we square 1.88, voila, we get the number 3.54. So in summary, Kepler's third law is the proportionality between a planet's orbital period and its distance from the Sun. And it's a very important mathematical relationship that ties together two very important concepts. At this point, I'd like to turn my attention to Galileo Galilei, because Galileo's contributions to modern astronomy were incredible. What's really important to note about Galileo, and what gave him a huge advantage in a scientific sense, was that he constructed an astronomical telescope. With a telescope, he could peer deeper into the heavens, and he could see objects much more closely and in much greater detail than anyone before him could. Galileo discovered the 4 large moons of Jupiter. He noted that the planets appeared as disks. He directly observed the phases of Venus that verified the heliocentric model of our solar system. He was capable of seeing features of the moon that nobody else could see with their naked eye. And he also discovered sunspots. And sunspots are areas of the sun's surface that are cooler than the surrounding areas. Well, if you watch sunspots long enough, you'll see them migrating across the sun's surface, and that's proof that the sun rotates. I'd like to briefly focus in on the picture showing the phases of Venus. As Galileo observed, Venus goes through a series of moon-like phases. During its full phase, Venus is furthest away from planet Earth, and that's why it looks smallest in the image you see here. But during Venus's crescent phase, it will look largest because it's closest to Earth. The point here is that both Earth and Venus orbit the Sun, and as Earth's position relative to Venus changes, we see Venus going through these particular phases. The final scientist I'd like to consider in this podcast is perhaps the most influential scientist in history, and that is Sir Isaac Newton. Now, Johannes Kepler made very important contributions to modern astronomy, but Kepler couldn't explain what caused planets to move around the Sun. Galileo also wrestled with this issue, And later in his life, Galileo started to put together a very good understanding of what's known as inertia, which I'll talk about in just a moment. Isaac Newton built off the ideas of his predecessors, and in order to explain the force that keeps planets moving about the sun, he had to literally invent calculus. There are two extremely important things you see on this slide. The first I'd like to overview is the law of universal gravitation, which states that every body in the universe attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square of the distance between them. What that means is that there's a gravitational force that exists between you and your desk, there's a gravitational force that exists between you and the moon, there's a gravitational force that exists between you and the earth, and there's even a gravitational force that exists between you and me. So if we build on this understanding of universal gravitation, there is a gravitational force that exists between the planets and the sun, and it's this force that tethers the planets to the sun in an elliptical orbit. Isaac Newton proved that the force of gravity, when combined with the tendency of a planet to remain in straight line motion, results in the elliptical orbits that Kepler discovered. Now let me build on this concept of planets wanting to remain in straight line motion. Because in order to explain this, we have to reference Newton's first law, which deals with inertia. Newton's first law states that an object at rest will stay at rest, and objects in motion will stay in motion unless they're acted upon by an outside force. But what's really important to note is that if the gravitational force between Earth and the Sun were somehow eliminated, Earth would move in a straight line path into deep outer space. I'd like to briefly show you a Phet simulation that illustrates this very idea. Before I hit play, the blue arrows you see on the screen represent the gravitational forces that exist between the Earth and the Sun. The gravitational force is always attractive, and that's why the two arrows are pointing at one another. The red arrow you see on the screen is Earth's velocity as it moves around the Sun. Now with the gravitational forces operating, Earth will follow an elliptical path as it orbits the Sun. But I want you to watch what happens as soon as I turn gravity off. As soon as the gravitational forces between the Earth and the Sun ceased to exist, Earth took off in a straight line path into the depths of outer space. So in summary, when we take inertia and Newton's law of universal gravitation collectively, you can almost think of Earth as falling around the Sun in its orbit, and it's the gravitational force that causes Earth to follow a curved path during its orbit. One final consideration in this Vodcast is a problem-solving situation that you may see on quizzes and tests. To the right side of the screen, you see three particular situations in which gravity is operating. Picture A shows two large objects fairly close together. Picture B shows a large object and a small object separated by a pretty great distance. And picture C shows a large object and a small object separated by a somewhat short distance. The first question is, which represents the strongest gravitational attraction? To answer this question, we have to know that the gravitational force is directly proportional to the masses of the two objects. The higher the mass of the two objects, the greater the gravitational attraction will be. But we should also realize that the gravitational force is inversely proportional to the square of the distance between them. What that basically means is the gravitational force will get smaller and smaller as objects get further away from each other. So our answer to the first question has to be choice A. The strongest gravitational attraction will exist between these two objects because they are the most massive and they're relatively close to one another. Now for the second question, which represents the weakest gravitational attraction, we have to keep in mind that if we're talking about similarly sized objects, the gravitational force between the two objects will be weaker if they're further apart. So the answer to the second question is choice B. Okay, that concludes this video podcast. In our next Vodcast, I will overview the origin of the solar system.